probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, that's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
The 5 Fingers of Evolution. A thorough understanding of biology requires a thorough understanding of the process of evolution. Most people are familiar with the process of natural selection. However, this is just one of 5 processes that can result in evolution. Before we discuss all 5 of these processes, we should define evolution. Evolution is simply change in the gene pool over time. But what is a gene pool? And, for that matter, what is a gene? Before spending any more time on genetics, let us begin with a story. Imagine that a boat capsizes and 10 survivors swim to shore on a deserted island. They are never rescued and they form a new population that exists for thousands of years. Strangely enough, 5 of the survivors have red hair. Red hair is created when a person inherits 2 copies of the red gene from their parents. If you only have 1 copy of the gene, you won't have red hair. To make this easier, we will assume that the 5 non-redheads are not carriers of the gene. The initial frequency of the red hair gene is therefore 50%, or 10 of 20 total genes. These genes are the gene pool. The 20 different genes are like cards in a deck that keep getting reshuffled with each new generation. Sex is simply a reshuffling of the genetic deck. The cards are reshuffled and passed to the next generation. The deck remains the same, 50% red. The genes are reshuffled and passed to the next generation. The gene pool remains the same, 50% red. Even though the population may grow in size over time, the frequency should stay at about 50%. If this frequency ever varies, then evolution has occurred. Evolution is simply change in the gene pool over time. Think about it in terms of the cards. If the frequency of the cards in the deck ever changes, evolution has occurred. There are 5 processes that can cause the frequency to change. To remember these processes, we will use the fingers on your hand, starting from the little finger and moving to the thumb. The little finger should remind you that the population can shrink. If the population shrinks, then chance can take over. For example, if only 4 individuals survive an epidemic, then their genes will represent the new gene pool. The next finger is the ring finger. This finger should remind you of mating because a ring represents a couple. If individuals choose a mate based on their appearance or location, the frequency may change. If red-headed individuals only mate with red-headed individuals, they could eventually form a new population. If no one ever mates with red-headed individuals, these genes could decrease. The next finger is the middle finger. The M in the middle finger should remind you of the M in the word mutation. If a new gene is added through mutation, it can affect the frequency. Imagine a gene mutation creates a new color of hair. This would obviously change the frequency in the gene pool. The pointer finger should remind you of movement. If new individuals flow into an area or immigrate, the frequency will change. If individuals flow out of an area or emigrate, then the frequency will change. In science, we refer to this movement as gene flow. All 4 of the processes represented by our fingers can cause evolution. Small population size, non-random mating, mutations, and gene flow. However, none of them lead to adaptation. Natural selection is the only process that creates organisms better adapted to their local environment. I use the thumb to remember this process. Nature votes thumbs up for adaptations that will do well in their environment and thumbs down to adaptations that will do poorly. The genes for individuals that are not adapted for their environment will gradually be replaced by those that are better adapted. Red hair is an example of one of these adaptations. Red hair is an advantage in the northern climates because the fair-skinned allowed ancestors to absorb more light and synthesize more vitamin D. Thumbs up. However, this was a disadvantage in the more southern climates where increased UV radiation led to cancer and decreased fertility. Thumbs down. Even the thumb itself is an adaptation formed through the process of natural selection. The evolution that we have described is referred to as microevolution because it refers to a small change. However, this form of evolution may eventually lead to macroevolution or speciation. Every organism on the planet shares ancestry with a single common ancestor. All living organisms on the planet are connected back in time through the process of evolution. Take a look at your own hand. It's an engineering masterpiece that was created by the 5 processes I just described over millions and millions of years. Can you recall the 5 main causes of evolution from memory? If you can't, hit rewind and watch that part again. But if you can, give yourself or your neighbor a big 5-fingered high five.
On a typical day at school, endless hours are spent learning the answers to questions. But right now, we'll do the opposite. We're going to focus on questions where you can't learn the answers because they're unknown. I used to puzzle about a lot of things as a boy. For example, what would it feel like to be a dog? Do fish feel pain? Well, how about insects? Was the Big Bang just an accident? I mean, is there a God? And if so, how are we so sure that it's a he and not a she? And why do so many innocent people and animals suffer terrible things? Is there really a plan for my life? Is the future yet to be written? Or is it already written? We just can't see it. But then, do I have free will? Who am I anyway? Am I just a biological machine? But then, why am I conscious? What is consciousness? Will robots become conscious one day? I mean, I kind of assumed that someday I would be told the answers to all these questions. I mean, someone must know, right? Guess what? No one knows. Most of those questions puzzle me more now than ever. But diving into them is exciting because it takes you to the edge of knowledge and you never know what you'll find there. So, 2 questions to kick off this series. Questions that no one on earth knows the answer to.
One of the funny things about owning a brain is that you have no control over the things that it gathers and holds on to, the facts and the stories. And as you get older, it only gets worse. Things stick around for years sometimes before you understand why you're interested in them, before you understand their import to you. Here's 3 of mine. When Richard Feynman was a young boy in Queens, he went for a walk with his dad and his wagon and a ball. And he noticed that when he pulled the wagon, the ball went to the back of the wagon. And he asked his dad, why does the ball go to the back of the wagon? And his dad said, that's inertia. He said, what's inertia? And his dad said, inertia is the name that scientists give to the phenomenon of the ball going to the back of the wagon. But in truth, nobody really knows. Feynman went on to earn degrees at MIT, Princeton. He solved the Challenger disaster. He ended up winning the Nobel Prize in physics for his Feynman diagrams describing the movement of subatomic particles. And he credits that conversation with his father as giving him a sense that the simplest questions could carry you out to the edge of human knowledge, and that that's where he wanted to play. And play he did. Now, Eratosthenes was the 3rd librarian at the Great Library at Alexandria, and he made many contributions to science. But the one he is most remembered for began in a letter that he received as the librarian from the town of Swenet, which was south of Alexandria. The letter included this fact that stuck in Eratosthenes' mind, and the fact was that the writer said at noon, on the solstice, when he looked down this deep well, he could see his reflection at the bottom, and he could also see that his head was blocking the sun. Now, I should tell you, the idea that Christopher Columbus discovered that the world is spherical is total bull. It's not true at all. In fact, everyone who was educated understood that the world was spherical since Aristotle's time, and Aristotle had proved it with a simple observation. He noticed that Every time you saw the Earth's shadow on the moon, it was circular. And the only shape that constantly creates a circular shadow is a sphere, QED. The Earth is round. But nobody knew how big it was until Eratosthenes got this letter with this fact. So he understood that the sun was directly above the city of Swenet, because looking down a well, it was a straight line all the way down the well, right past the guy's head, up to the sun. Eratosthenes knew another fact. He knew that a stick stuck in the ground in Alexandria at the same time and the same day at noon, the sun's zenith, on the solstice, the sun cast a shadow that showed it was 7.2 degrees off axis. Now, if you know the circumference of a circle and you have 2 points on it, all you need to know is the distance between those 2 points, and you can extrapolate the circumference. 360 degrees divided by 7.2 equals 50. I know it's a little bit of a round number, and it makes me suspicious of this story too, but it's a good story, so we'll continue with it. He needed to know the distance between Swenet and Alexandria, which is good because Eratosthenes was good at geography. In fact, he invented the word geography. The road between Swenet and Alexandria was a road of commerce, and commerce needed to know how long it took to get there. It needed to know the exact distance, so he knew very precisely that the distance between the two cities was 500 miles. Multiply that times 50, you get 25,000, which is within 1% of the actual diameter of the Earth. He did this 2,200 years ago. Now, we live in an age where multi-billion-dollar pieces of machinery are looking for the Higgs boson. We're discovering particles that may travel faster than the speed of light. And all of these discoveries are made possible by technology that's been developed in the last few decades. But for most of human history, we had to discover these things using our eyes and our ears and our minds. Armand Fizeau was an experimental physicist in Paris. His specialty was actually refining and confirming other people's results. And this might sound like a bit of an also-ran, but in fact this is the soul of science, because there's no such thing as a fact that cannot be independently corroborated. And he was familiar with Galileo's experiments in trying to determine whether or not light had a speed. So Galileo had worked out this really wonderful experiment where he and his assistant had a lamp. Each one was holding a lamp, and Galileo would open his lamp and his assistant would open his lamp. And they got the timing down really good. They just knew their timing. And then they stood at two hilltops 2 miles distant. And they did the same thing on the assumption from Galileo that if light had a discernible speed, he'd notice a delay in the light coming back from his assistant's lamp. But light was too fast for Galileo. He was off by several orders of magnitude when he assumed that light was roughly 10 times as fast as the speed of sound. Fizeau was aware of this experiment. He lived in Paris, and he set up 2 experimental stations roughly 5.5 miles distant in Paris. And he solved this problem of Galileo's, and he did it with a really relatively trivial piece of equipment. He did it with one of these. I'm going to put away the clicker for a second because I want to engage your brains in this. Now, this is a toothed wheel. It's got a bunch of notches, and it's got a bunch of teeth. This was Fizeau's solution to sending discrete pulses of light. He put a beam behind one of these notches. If I point a beam through this notch at a mirror 5 miles away, that beam is bouncing off the mirror and coming back to me through this notch. But something interesting happens. As he spins the wheel faster, he notices that it seems like a door is starting to close on the light beam that's coming back to his eye. Why is that? It's because the pulse of light, it's not coming back through the same notch. It's actually hitting a tooth. And he spins the wheel fast enough, and he fully occludes the light. And then, based on the distance between the 2 stations and the speed of his wheel and the number of notches in the wheel, he calculates the speed of light to within 2% of its actual value. And he does this in 1849. This is what really gets me going about science. Whenever I'm having trouble understanding a concept, I go back and I research the people that discovered that concept. I look at the story of how they came to understand it. And what happens when you look at what the discoverers were thinking about when they made their discoveries is you understand that they are not so different from us. We are all bags of meat and water. We all start with the same tools. I love the idea that different branches of science are called fields of study. Most people think of science as a closed black box, and in fact, it is an open field, and we are all explorers. The people that made these discoveries just thought a little bit harder about what they were looking at, and they were a little bit more curious. And their curiosity changed the way people thought about the world, and thus it changed the world. They changed the world, and so can you. Thank you.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper, separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste, but the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation-reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall, rather than expending one battery to charge another, is your best bet to forestall that fatal bleep.
So I'm here today to encourage you to think about New York City, and not just as one of humanity's greatest achievements, but as home to native wildlife that are subject to a grand evolutionary experiment. So take this forested hillside in northern Manhattan, for example. This is one of the last areas left in the city where there's clean spring water that's still seeping out of the ground. You could drink this out of your hands, you'd be okay. These tiny little areas of seeping water contain huge populations of northern dusky salamanders. These guys were common in the city maybe 60 years ago, but now they're just stuck on this single hillside in a few places in Staten Island. Not only do they suffer the indignity of being stuck on this hillside, but we divided that hillside in two on two different occasions with bridges crossing from the Bronx into Manhattan. But they're still there on either side of the bridges where you see the red arrows, about 180th Street, 167th Street. And my lab has found that if you just take a few segments of DNA from salamanders in those two locations, you can tell which side of the bridge they came from. We built this single piece of infrastructure that's changed their evolutionary history. We can go study these guys. We just go to the hillside, we know where they are, we flip over rocks so we can catch them. There are a lot of other things in New York City, though, that are not that easy to capture, such as this guy, Coyote. We caught him on an automatic camera trap somewhere in an undisclosed location. I'm not allowed to talk about it yet. But they're moving into New York City for the first time. They're very flexible, intelligent animals. This is one of this year's pups checking out one of our cameras. And my colleagues and I are very interested in understanding how they're going to spread through the area, how they're going to survive here, and maybe even thrive. And they're probably coming to a neighborhood near you if they're not already there. So there's some things that are too fast to be caught by hand. We can't pick them up on the cameras. So we actually set out traps all around New York City in the parks. This is one of our most common activities. Here's some of my students and collaborators getting the traps out ready. And this guy we catch in almost every forested area in New York City. This is the white-footed mouse. This is not the mouse you find running around your apartment. This is a native species, been here long before humans, and you find them in forests and meadows. Because they're so common in forested areas in the city, we're using them as a model to understand how species are adapting to urban environments. So if you think back 400 years ago, the 5 boroughs would have been covered in forest and other types of vegetation. This mouse would have been everywhere. Huge populations that showed few genetic differences across the landscape. But if you look at the situation today, they're just stuck in these little islands of forest scattered around the city. Just using 18 short segments of DNA, we can pretty much take a mouse, somebody could give us a mouse, not tell us where it was from, and we could determine what park it came from. That's how different they become. You'll notice in the middle of this colored figure here, there's some mixed up colors. There are a few parks in the city that are still connected to each other with strips of forest, so that the mice can run back and forth and spread their genes so they don't become different. But throughout the city, they're mostly becoming different in the parks. All right, so I'm telling you they're different, but what does that really mean? What's changing about their biology? To answer this question, we're sequencing thousands of genes from our city mice and comparing those to thousands of genes from the country mice, so their ancestors outside of New York City in these big, more wilderness areas. Now, genes are short segments of DNA that code for amino acids. And amino acids are the building blocks of proteins. Now, if a single base pair changes in a gene, you can get a different amino acid, which will then change the shape and structure of the protein. If you change the structure of a protein, you often change something about what it does in the organism. Now, if that change leads to a longer life or more babies for a mouse, something evolutionary biologists call fitness, then that single base pair change will spread quickly in an urban population. So this crazy figure is actually called a Manhattan plot because it kind of looks like a skyline. And each dot represents one gene. And the higher the dot is in the plot, the more different it is between city and country mice. The ones kind of at the tips of the skyscrapers are the most different, especially those above the red line. And these genes encode for things like immune response to disease, so there might be more disease in very dense urban populations, metabolism, how the mice use energy, and heavy metal tolerance. You guys could probably predict that New York City soils are pretty contaminated with lead and chromium and that sort of thing. And now our hard work is really starting. We're going back into the wilds of New York City parks, following the lives of individual mice and seeing exactly what these genes are doing for them. And I would encourage you guys to try to look at your parks in a new way. I'm not going to be the next Charles Darwin, but one of you guys might be, so just keep your eyes open. Thank you.
Would mathematics exist if people didn't? Since ancient times, mankind has hotly debated whether mathematics was discovered or invented. Did we create mathematical concepts to help us understand the universe around us? Or is math the native language of the universe itself, existing whether we find its truths or not? Are numbers, polygons, and equations truly real, or merely ethereal representations of some theoretical ideal? The independent reality of math has some ancient advocates. The Pythagoreans of 5th century Greece believed numbers were both living entities and universal principles. They called the number 1 the monad, the generator of all other numbers and source of all creation. Numbers were active agents in nature. Plato argued mathematical concepts were concrete and as real as the universe itself, regardless of our knowledge of them. Euclid, the father of geometry, believed nature itself was the physical manifestation of mathematical laws. Others argue that while numbers may or may not exist physically, mathematical statements definitely don't. Their truth values are based on rules that humans created. Mathematics is thus an invented logic exercise, with no existence outside mankind's conscious thought, a language of abstract relationships based on patterns discerned by brains, built to use those patterns to invent useful but artificial order from chaos. One proponent of this sort of idea was Leopold Kronecker, a professor of mathematics in 19th century Germany. His belief is summed up in his famous statement, "God created the natural numbers. All else is the work of man." During mathematician David Hilbert's lifetime, there was a push to establish mathematics as a logical construct. Hilbert attempted to axiomatize all of mathematics, as Euclid had done with geometry. He and others who attempted this saw mathematics as a deeply philosophical game, but a game nonetheless. Henri Poincaré, one of the fathers of non-Euclidean geometry, believed that the existence of non-Euclidean geometry, dealing with the non-flat surfaces of hyperbolic and elliptical curvatures, proved that Euclidean geometry, the long-standing geometry of flat surfaces, was not a universal truth, but rather one outcome of using one particular set of game rules. But in 1960, Nobel Physics laureate Eugene Wigner coined the phrase the unreasonable effectiveness of mathematics, pushing strongly for the idea that mathematics is real and discovered by people. Wigner pointed out that many purely mathematical theories, developed in a vacuum, often with no view towards describing any physical phenomena, have proven decades or even centuries later to be the framework necessary to explain how the universe has been working all along. For instance, the number theory of British mathematician Godfrey Hardy, who had boasted that none of his work would ever be found useful in describing any phenomena in the real world, helped establish cryptography. Another piece of his purely theoretical work became known as the Hardy-Weinberg law in genetics and won a Nobel Prize. And Fibonacci stumbled upon his famous sequence while looking at the growth of an idealized rabbit population. Mankind later found the sequence everywhere in nature, from sunflower seeds and flower petal arrangements to the structure of a pineapple, even the branching of bronchi in the lungs. Or there's the non-Euclidean work of Bernhard Riemann in the 1850s, which Einstein used in the model for general relativity a century later. Here's an even bigger jump. Mathematical knot theory, first developed around 1771 to describe the geometry of position, was used in the late 20th century to explain how DNA unravels itself during the replication process. It may even provide key explanations for string theory. Some of the most influential mathematicians and scientists of all of human history have chimed in on the issue as well, often in surprising ways. So, is mathematics an invention or a discovery? Artificial construct or universal truth? Human product or natural, possibly divine creation? These questions are so deep, the debate often becomes spiritual in nature. The answer might depend on the specific concept being looked at, but it can all feel like a distorted Zen koan. If there's a number of trees in a forest, but no one's there to count them, does that number exist?
Flying through the night, I watch over this world. A silent guardian, a watchful protector, a dark knight.
Okay, fine, so I'm not Batman. I'm just a bat. But like Batman, I'm often misunderstood. People think I'm scary, strange, and dangerous. If they only knew my story, though, I'd be cheered as a hero. When people think of bats, many think of vampires who want to suck their blood. But the truth is that out of over 1,200 bat species, only 3 are vampire bats. Out of these 3, only 1 prefers the blood of mammals. And even these bats mostly feed on cattle. Maybe that still doesn't seem so great, but vampire bats can be a great help to humans. A chemical known as desmoteplase found in vampire bat saliva helps break down blood clots and is being tested by recovering stroke victims. Of the remaining 1,000+ species of bats, about 70% feed on insects. These bats help control the real vampires, mosquitoes, whose nasty bites are not just annoying, but spread diseases like West Nile virus. A single little brown bat can eat 1,000 insects every hour, and a colony of Mexican free-tailed bats can eat several tons of moths in just one night. In the United States alone, bats provide an estimated $3.7 billion worth of free pest control for farmers, which benefits everyone who eats the foods that they grow. Fruit bats, also called megabats because of their large size, are important for the role they play in plant pollination. By traveling between flowers while feeding on nectar and fruits, these bats transport the pollen and seeds that help plants reproduce. In Southeast Asia, for example, the cave nectar bat is the only pollinator of the durian fruit. Other bats pollinate peaches, bananas, and the agave plants that tequila is made from. Without them, many of our food plants would be unable to produce the tasty fruits we enjoy. As heroes of the ecosystem, bats have their own unique utility belts. Bats have been a source of inspiration for the design of flying robots and even an energy-efficient spy plane, as they are the only mammal capable of true powered flight. Echolocation, a type of biological sonar, is also used by bats as a way to navigate and find prey in the dark. Although there's a common misconception that bats are blind, in truth, all species of bats have sight, and some have even adapted large eyes to see better in dim lighting. Many people worry about getting infected by bats, and like any other animals, bats can carry diseases like rabies. In reality, though, less than 0.5% of all bats carry this virus. That's about the same odds as getting the same result on a coin flip 8 times in a row. The perception that bats are often diseased may come from the fact that sick bats, who may show unusual behavior, emerge during the daytime, or be unable to fly, are more likely to be encountered by people. So a good way to protect yourself is to protect bats as well, keeping them healthy, protecting their habitats, and reducing their risk of transmitting disease. In North America, bats are threatened by a devastating sickness called white nose syndrome. This fungal infection causes bats to wake up while hibernating during the winter. Unable to find food, they expend large amounts of energy and eventually starve to death. White nose syndrome has wiped out entire caves full of bats, with a mortality rate that can exceed 90%. Climate change and habitat destruction also pose serious threats to bat populations. For example, in January 2014, a record heat wave in Australia caused over 100,000 bats to die from heat exhaustion. Some people just want to watch the world burn, and bats all over the world are threatened by damage to the places that we call home, including mangrove swamps, old-growth forests, and of course, bat caves. So even though I'm the hero of the story, I do need to be saved. And now that you know the true story about us bats, you can learn how to protect such heroic animals. Install a properly designed bat box, one of the easiest ways to provide shelter for bats. Discourage the use of pesticides, which can harm bats when we try to feed on the insects you want to get rid of in the first place. Avoid going into caves where you might disturb hibernating bats, and always decontaminate your gear after visiting a cave. If you have unwanted bats living in an attic or barn, contact your local government to safely and humanely relocate us. And if you come across a bat, do not attempt to handle it, but instead call animal control. Batman might want to keep his identity secret, but a great way to help real bats is by continuing to learn about them and spreading the truth that they are real heroes, even if their good deeds are often unseen. You've probably heard that carbon dioxide is warming the Earth. But how does it work? Is it like the glass of a greenhouse? Or like an insulating blanket? Well, not entirely. The answer involves a bit of quantum mechanics. But don't worry, we'll start with a rainbow. If you look closely at sunlight separated through a prism, you'll see dark gaps where bands of color went missing. Where did they go? Before reaching our eyes, different gases absorbed those specific parts of the spectrum. For example, oxygen gas snatched up some of the dark red light, and sodium grabbed 2 bands of yellow. But why do these gases absorb specific colors of light? This is where we enter the quantum realm. Every atom and molecule has a set number of possible energy levels for its electrons. To shift its electrons from the ground state to a higher level, a molecule needs to gain a certain amount of energy. No more, no less. It gets that energy from light, which comes in more energy levels than you could count. Light consists of tiny particles called photons, and the amount of energy in each photon corresponds to its color. Red light has lower energy and longer wavelengths. Purple light has higher energy and shorter wavelengths. Sunlight offers all the photons of the rainbow, so a gas molecule can choose the photons that carry the exact amount of energy needed to shift the molecule to its next energy level. When this match is made, the photon disappears as the molecule gains its energy, and we get a small gap in our rainbow. If a photon carries too much or too little energy, the molecule has no choice but to let it fly past. This is why glass is transparent. The atoms in glass do not pair well with any of the energy levels in visible light, so the photons pass through. So which photons does carbon dioxide prefer? Where is the black line in our rainbow that explains global warming? Well, it's not there. Carbon dioxide doesn't absorb light directly from the sun. It absorbs light from a totally different celestial body, one that doesn't appear to be emitting light at all: Earth. If you're wondering why our planet doesn't seem to be glowing, it's because the Earth doesn't emit visible light. It emits infrared light. The light that our eyes can see, including all of the colors of the rainbow, is just a small part of the larger spectrum of electromagnetic radiation, which includes radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays. It may seem strange to think of these things as light, but there is no fundamental difference between visible light and other electromagnetic radiation. It's the same energy, but at a higher or lower level. In fact, it's a bit presumptuous to define the term visible light by our own limitations. After all, infrared light is visible to snakes, and ultraviolet light is visible to birds. If our eyes were adapted to see light of 1900 megahertz, then a mobile phone would be a flashlight, and a cell phone tower would look like a huge lantern. Earth emits infrared radiation because every object with a temperature above absolute zero will emit light. This is called thermal radiation. The hotter an object gets, the higher frequency the light it emits. When you heat a piece of iron, it will emit more and more frequencies of infrared light, and then, at a temperature of around 450 degrees Celsius, its light will reach the visible spectrum. At first, it will look red hot, and with even more heat, it will glow white with all of the frequencies of visible light. This is how traditional light bulbs were designed to work, and why they're so wasteful. 95% of the light they emit is invisible to our eyes. It's wasted as heat. Earth's infrared radiation would escape to space if there weren't greenhouse gas molecules in our atmosphere. Just as oxygen gas prefers the dark red photons, Carbon dioxide and other greenhouse gases match with infrared photons. They provide the right amount of energy to shift the gas molecules into their higher energy level. Shortly after a carbon dioxide molecule absorbs an infrared photon, it will fall back to its previous energy level and spit a photon back out in a random direction. Some of that energy then returns to Earth's surface, causing warming. The more carbon dioxide in the atmosphere, the more likely that infrared photons will land back on Earth and change our climate. Think about all the things that need to happen for a human settlement to thrive. Obtaining food, building shelter, raising children, and more. There needs to be a way to divide resources, organize major efforts, and distribute labor efficiently. Now imagine having to do this without any sort of planning or higher-level communication. Welcome to the ant colony. Ants have some of the most complex social organization in the animal kingdom, living in structured colonies containing different types of members who perform specific roles. But although this may sound similar to some human societies, this organization doesn't arise from any higher-level decisions, but is part of a biologically programmed cycle. In many species, all the winged males and winged virgin queens from all the nearby colonies in the population each leave from their different nests and meet at a central place to mate, using pheromones to guide each other to a breeding ground. After mating, the males die off, while females try to establish a new colony. The few that are successful settle down in a suitable spot, lose their wings, and begin laying eggs, selectively fertilizing some using stored sperm they've saved up from mating. Fertilized eggs grow into female workers who care for the queen and her eggs, build and defend the colony, and forage for food, while unfertilized eggs grow into males whose only job is to wait until they are ready to leave the nest and reproduce, beginning the cycle again. So how do worker ants decide what to do and when? Well, they don't really. Although they have no methods of intentional communication, individual ants do interact with one another through touch, sound, and chemical signals. These stimuli accomplish many things, from serving as an alarm to other ants if one is killed, to signaling when a queen is nearing the end of her reproductive life. But one of the most impressive collective capabilities of an ant colony is to thoroughly and efficiently explore large areas without any predetermined plan. Most species of ants have little or no sense of sight and can only smell things in their vicinity. Combined with their lack of high-level coordination, this would seem to make them terrible explorers. But there is an amazingly simple way that ants maximize their searching efficiency, by changing their movement patterns based on individual interactions. When two ants meet, they sense each other by touching antennae. If there are many ants in a small area, this will happen more often, causing them to respond by moving in more convoluted, random paths in order to search more thoroughly. But in a larger area with less ants, where such meetings happen less often, they can walk in straight lines to cover more ground. While exploring their environment in this way, an ant may come across any number of things, from threats or enemies to alternate nesting sites. And some species have another capability known as recruitment. When one of these ants happens to find food, it will return with it, marking its path with a chemical scent. Other ants will then follow this pheromone trail, renewing it each time they manage to find food and return. Once the food in that spot is depleted, the ants stop marking their return, the scent dissipates, and ants are no longer attracted to that path. These seemingly crude methods of search and retrieval are in fact so useful that they are applied in computer models to obtain optimal solutions from decentralized elements, working randomly and exchanging simple information. This has many theoretical and practical applications, from solving the famous traveling salesman problem to scheduling computing tasks and optimizing internet searches, to enabling groups of robots to search a minefield or a burning building collectively without any central control. But you can observe these fascinatingly simple yet effective processes directly through some simple experiments by allowing ants to enter empty spaces of various sizes and paying attention to their behavior. Ants may not be able to vote, hold meetings, or even make any plans, but we humans may still be able to learn something from the way that such simple creatures are able to function so effectively in such complex ways. Think about all the things that need to happen for a human settlement to thrive. Obtaining food, building shelter, raising children, and more. There needs to be a way to divide resources, organize major efforts, and distribute labor efficiently. Now imagine having to do this without any sort of planning or higher-level communication. Welcome to the ant colony. Ants have some of the most complex social organization in the animal kingdom, living in structured colonies containing different types of members who perform specific roles. But although this may sound similar to some human societies, this organization doesn't arise from any higher-level decisions, but is part of a biologically programmed cycle. In many species, all the winged males and winged virgin queens from all the nearby colonies in the population each leave from their different nests and meet at a central place to mate, using pheromones to guide each other to a breeding ground. After mating, the males die off, while females try to establish a new colony. The few that are successful settle down in a suitable spot, lose their wings, and begin laying eggs, selectively fertilizing some using stored sperm they've saved up from mating. Fertilized eggs grow into female workers who care for the queen and her eggs, build and defend the colony, and forage for food, while unfertilized eggs grow into males whose only job is to wait until they are ready to leave the nest and reproduce, beginning the cycle again. So how do worker ants decide what to do and when? Well, they don't really. Although they have no methods of intentional communication, individual ants do interact with one another through touch, sound, and chemical signals. These stimuli accomplish many things, from serving as an alarm to other ants if one is killed, to signaling when a queen is nearing the end of her reproductive life. But one of the most impressive collective capabilities of an ant colony is to thoroughly and efficiently explore large areas without any predetermined plan. Most species of ants have little or no sense of sight and can only smell things in their vicinity. Combined with their lack of high-level coordination, this would seem to make them terrible explorers. But there is an amazingly simple way that ants maximize their searching efficiency, by changing their movement patterns based on individual interactions. When two ants meet, they sense each other by touching antennae. If there are many ants in a small area, this will happen more often, causing them to respond by moving in more convoluted, random paths in order to search more thoroughly. But in a larger area with less ants, where such meetings happen less often, they can walk in straight lines to cover more ground. While exploring their environment in this way, an ant may come across any number of things, from threats or enemies to alternate nesting sites. And some species have another capability known as recruitment. When one of these ants happens to find food, it will return with it, marking its path with a chemical scent. Other ants will then follow this pheromone trail, renewing it each time they manage to find food and return. Once the food in that spot is depleted, the ants stop marking their return, the scent dissipates, and ants are no longer attracted to that path. These seemingly crude methods of search and retrieval are in fact so useful that they are applied in computer models to obtain optimal solutions from decentralized elements, working randomly and exchanging simple information. This has many theoretical and practical applications, from solving the famous traveling salesman problem to scheduling computing tasks and optimizing internet searches, to enabling groups of robots to search a minefield or a burning building collectively without any central control. But you can observe these fascinatingly simple yet effective processes directly through some simple experiments by allowing ants to enter empty spaces of various sizes and paying attention to their behavior. Ants may not be able to vote, hold meetings, or even make any plans, but we humans may still be able to learn something from the way that such simple creatures are able to function so effectively in such complex ways.
The phenomenon you saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor. Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So, a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So, electricity is the flow of electrons inside the material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation. It's quite remarkable. Think about it. In classical physics, there is always some friction, some energy loss, but not here, because it is a quantum effect. But that's not all, because superconductors don't like magnetic fields. So a superconductor will try to expel magnetic fields from the inside. And it has the means to do that by circulating currents. Now, the combination of both effects, the expulsion of magnetic fields and zero electrical resistance, is exactly a superconductor. But the picture isn't always perfect, as we all know, and sometimes strands of magnetic field remain inside the superconductor. Now, under proper conditions, which we have here, these strands of magnetic field can be trapped inside the superconductor. And these strands of magnetic field inside the superconductor, they come in discrete quantities. Why? Because it is a quantum phenomenon. It's quantum physics. And it turns out that they behave like quantum particles. In this movie here, you can see how they flow one by one discretely. This is strands of magnetic field. These are not particles, but they behave like particles. So this is why we call this effect quantum levitation and quantum locking. But what happens to the superconductor when we put it inside a magnetic field? Well, first there are strands of magnetic field left inside, but now the superconductor doesn't like them moving around because their movement dissipates energy, which breaks the superconductivity state. So what it actually does, it locks these strands, which are called fluxons, and it locks these fluxons in place. And by doing that, what it actually does is locking itself in place. Why? Because any movement of the superconductor will change their place, will change their configuration. So we get quantum locking. And let me show you how this works. I have here a superconductor, which I wrapped up so it stays cold long enough. And when I place it on top of a regular magnet, it just stays locked in midair. Now, this is not just levitation, it's not just repulsion. I can rearrange the fluxons and it will be locked in this new configuration, like this, or move it slightly to the right or to the left. So, this is quantum locking, actually locking, three-dimensional locking of the superconductor. Now, of course, I can turn it upside down, and it will remain locked. Now that we understand that this levitation, so-called levitation, is actually locking, yeah, we understand that. You won't be surprised to hear that if I take this circular magnet, in which the magnetic field is the same all around, the superconductor will be able to freely rotate around the axis of the magnet. Why? Because as long as it rotates, the locking is maintained. You see, I can adjust and I can rotate the superconductor. We have frictionless motion. It is still levitating, but can move freely all around. So, we have quantum locking, and we can levitate it on top of this magnet. But how many fluxons, how many magnetic strands are there in a single disk like this? Well, we can calculate it, and it turns out quite a lot. 100 billion strands of magnetic field inside this 3-inch disk. But that's not the amazing part yet, because there is something I haven't told you yet. And and the amazing part is that this superconductor that you see here is only half a micron thick. It's extremely thin. And this extremely thin layer is able to levitate more than 70,000 times its own weight. It's a remarkable effect. It's very strong. Now, I can extend this circular magnet and make whatever track I want. For example, I can make a large circular rail here. And when I place the superconducting disk on top of this rail, it moves freely. And again, that's not all. I can adjust its position like this and rotate, and it freely moves in this new position. And I can even try a new thing. Let's try it for the first time. I can take this disk and put it here. And while it stays here, don't move, I will try to rotate the track. And hopefully, if I did it correctly, it stays suspended. You see, it's quantum locking, not levitation. Now, while I'll let it circulate for a little more, let me tell you a little bit about superconductors. Now, so, we now know that we are able to transfer enormous amount of currents inside superconductors. So we can use them to produce strong magnetic fields, such as needed in MRI machine, particle accelerators, and so on. But we can also store energy using superconductors, because we have no dissipation. And we could also produce power cables to transfer enormous amount of current between power stations. Imagine you could back up a single power station with a single superconducting cable. But what is the future of quantum levitation and quantum locking? Well, let me answer this simple question by giving you an example. Imagine you would have a disc similar to the one I have here in my hand, 3-inch diameter, with a single difference. The superconducting layer, instead of being half a micron thin, being 2 millimeter thin, quite thin. This 2 millimeter thin superconducting layer could hold 1,000 kilograms. A small car in my hand. Amazing. Thank you.
I want you guys to imagine that you're a soldier running through the battlefield. Now you're shot in the leg with a bullet, which severs your femoral artery. Now this bleed is extremely traumatic and can kill you in less than 3 minutes. Unfortunately, by the time that a medic actually gets to you, what the medic has on his or her belt can take 5 minutes or more with the application of pressure to stop that type of bleed. Now, this problem is not only a huge problem for the military, but it's also a huge problem that's epidemic throughout the entire medical field, which is how do we actually look at wounds and how do we stop them quickly in a way that can work with the body. So now what I've been working on for the last 4 years is to develop smart biomaterials, which are actually materials that will work with the body, helping it to heal and helping it to allow the wounds to heal normally. So now, before we do this, we have to take a much closer look at actually how does the body work. So now everybody here knows that the body is made up of cells. So the cell is the most basic unit of life, but not many people know what else. So it actually turns out that your cells sit in this mesh of complicated fibers, proteins, and sugars known as the extracellular matrix. So now the ECM is actually this mesh that holds the cells in place, provides structure for your tissues, but it also gives the cells a home. It allows them to feel what they're doing, where they are, and tells them how to act and how to behave. And it actually turns out that the extracellular matrix is different from every single part of the body. So the ECM in my skin is different than the ECM in my liver. And the ECM in different parts of the same organ actually vary. So it's very difficult to be able to have a product that'll react to the local extracellular matrix, which is exactly what we're trying to do. So now, for example, think of the rainforest. You have the canopy, you have the understory, and you have the forest floor. Now, all of these parts of the forest are made up of different plants, and different animals call them home. So just like that, the extracellular matrix is incredibly diverse in 3 dimensions. On top of that, the extracellular matrix is responsible for all wound healing. So if you imagine cutting the body, you actually have to rebuild this very complex ECM in order to get it to form again. And a scar, in fact, is actually poorly formed extracellular matrix. So now behind me is an animation of the extracellular matrix. So if you see your cells sit in this complicated mesh, and as you move throughout the tissue, the extracellular matrix changes. So now every other piece of technology on the market can only manage a 2-dimensional approximation of the extracellular matrix, which means that it doesn't fit in with the tissue itself. So when I was a freshman at NYU, what I discovered was you can actually take small pieces of plant-derived polymers and reassemble them onto the wound. So if you have a bleeding wound like the one behind me, you can actually put our material onto this, and just like Lego blocks, it'll reassemble into the local tissue. So that means if you put it onto liver, it turns into something that looks like liver, and if you put it onto skin, it turns into something that looks just like skin. So when you put the gel on, it actually reassembles into this local tissue. So now, this has a whole bunch of applications, but basically the idea is wherever you put this product, you're able to reassemble into it immediately. Now this is a simulated arterial bleed, blood warning, at twice human artery pressure. So now this type of bleed is incredibly traumatic, and like I said before, would actually take 5 minutes or more with pressure to be able to stop. Now in the time that it takes me to introduce the bleed itself, our material is able to stop that bleed. And it's because it actually goes on and works with the body to heal. So it reassembles into this piece of meat. And then the blood actually recognizes that that's happening and produces fibrin, producing a very fast clot in less than 10 seconds. So now this technology, thank you. So now this technology, by January, will be in the hands of veterinarians, and we're working very diligently to try to get it into the hands of humans, hopefully within the next year. But really, once again, I want you guys to imagine that you're a soldier running through a battlefield. Now you get hit in the leg with a bullet, and instead of bleeding out in 3 minutes, you pull a small pack of gel out of your belt, and with the press of a button, you're able to stop your own bleed, and you're on your way to recovery. Thank you very much.
I'm here to show you how something you can't see can be so much fun to look at. You're about to experience a new, available, and exciting technology that's going to make us rethink how we waterproof our lives. What I have here is a cinder block that we've coated half with a nanotechnology spray that can be applied to almost any material. It's called Ultra EverDry. And when you apply it to any material, it turns into a super hydrophobic shield. So this is a cinder block, uncoated, and you can see that it's porous. It absorbs water. Not anymore. Porous, non-porous. So what's super hydrophobic? Super hydrophobic is how we measure a drop of water on a surface. The rounder it is, the more hydrophobic it is. And if it's really round, it's super hydrophobic. A freshly waxed car, the water molecules slump to about 90 degrees. A windshield coating is going to give you about 110 degrees. But what you're seeing here is 160 to 175 degrees, and anything over 150 is super hydrophobic. So as part of the demonstration, what I have is a pair of gloves, and we've coated one of the gloves with the nanotechnology coating. And let's see if you can tell which one, and I'll give you a hint. Did you guess the one that was dry? When you have a nanotechnology and nanoscience, what's occurred is that we're able to now look at atoms and molecules and actually control them for great benefits. And we're talking really small here. The way you measure nanotechnology is in nanometers, and 1 nanometer is a billionth of a meter. And to put some scale to that, if you had a nanoparticle that was 1 nanometer thick, and you put it side by side, and you had 50,000 of them, you'd be the width of a human hair. So very small, but very useful. And it's not just water that this works with. It's a lot of water-based materials like concrete, water-based paint, mud, and also some refined oils as well. You can see the difference. Moving on to the next demonstration, we've taken a pane of glass and we've coated the outside of it, we've framed it with the nanotechnology coating. And we're going to pour this green tinted water inside the middle, and you're going to see it's going to spread out on glass like you normally think it would, except when it hits the coating, it stops. And I can't even coax it to leave. It's that afraid of the water. So what's going on here? What's happening? Well, the surface of the spray coating is actually filled with nanoparticles that form a very rough and craggly surface. You'd think it'd be smooth, but it's actually not. And it has billions of interstitial spaces. And those spaces, along with the nanoparticles, reach up and grab the air molecules and cover the surface with air. It's an umbrella of air all across it. And that layer of air is what the water hits, the mud hits, the concrete hits, and it glides right off. So if I put this inside this water here, you can see a silver reflective coating around it. And that silver reflective coating is the layer of air that's protecting the water from touching the paddle, and it's dry. So what are the applications? I mean, many of you right now are probably going through your head. Everyone that sees this gets excited and says, oh, I could use it for this and this and this. The applications, in a general sense, could be anything that's anti-wetting. We've certainly seen that today. It could be anything that's anti-icing, because if you don't have water, you don't have ice. It could be anti-corrosion. No water, no corrosion. It could be antibacterial. Without water, the bacteria won't survive. And it could be things that need to be self-cleaning as well. So, imagine how something like this could help revolutionize your field of work. And I'm going to leave you with one last demonstration, but before I do that, I would like to say thank you and think small. It's going to happen. Wait for it. Wait for it.
You guys didn't hear about us cutting out the design from Ted? He ran into all sorts of problems in terms of managing the medical research part. It's happening!
There's one thing I believe in this world. It's that the chupacabra is real and he's hiding in our hair. And I also, if there are two things that I believe, it's that we can learn so much from our children. You know, kids have an interesting take on just about anything. They see things in a way that we as adults can't. You know, we have prejudices, we have preconceived notions, we have all sorts of things like that. So I recently sat down with a group of young people to ask them what the difference is between boys and girls. This is something I've actually been wondering about for years. And as you will see here, I got some exceptionally enlightening answers. What's the difference between a boy and a girl?
Well, boys like doing like rough sort of stuff, and girls like doing kind of like kind and soft.
Girls are gentle.
Yeah.
And boys are vicious animals.
Yeah.
The boy has thicker hair than the girl.
Thicker?
Thick.
Sometimes, yeah.
Sometimes. The boys wear yarmulke.
Boys wear yarmulke, right?
And girls don't.
That's right.
You can tell by the Adam's apple, because if they don't have an Adam's apple, then it's a girl. But if they do, then it's a boy.
That's right. That's absolutely right.
Girls like pink, boys don't.
Sometimes boys like pink, and sometimes girls don't like pink, right? Yeah.
Girls shop a lot, boys don't.
Sometimes boys shop a lot, though.
Boys like to watch TV a lot, and girls don't.
They don't? I think some girls do.
This is hard.
Yeah, this is a difficult one. We could dance around this forever, right?
Yeah.
Yeah, you and I, yeah.
I know a way, but I think it's really disturbing.
What is disturbing?
You know how you tell a boy pup from a girl pup? You know when people hit their thing in between their legs, you know how they say, "Oh, my nuts."
What?
Oh, my nuts. They actually mean
Who said this?
I'm just trying to express what the question you asked
okay.
me.
No, you go ahead. So again, what's the difference between a boy and a girl?
Well, I shouldn't say the disturbing way, but most girls have longer hair than boys.
90%.
Well done. What is the difference between a boy and a girl?
Get me she was talking about something.
What?
She was saying something in the car that it's a little about potty words that but
Oh, well, tell us then, for sure. What is it?
It was weenus, penis, cupid, stupid.
It was weenus, penis, cupid, stupid?
Yeah.
Is this a song?
No, it's a poem my friend
Oh, it's
made
a
up
poem?
when we were finding funny rhymes.
Oh, well, that's a pretty funny one, right? So what's different about boys and girls?
Hair is longer than, and their privates are different.
Right.
Yeah, they're called differently. Penis and vagina.
Finally, some honesty.
Penis, penis, stupid, stupid.
Albert Einstein, the icon of genius. Why? Because he figured out E equals MC squared? Because he didn't like socks? Nope, because he came up with the most powerful idea in science, general relativity. His masterpiece is now 100 years old, and while the physicists are partying, the rest of us are left wondering what the f*** it's all about. Well, here goes. At 26, he figured out nothing less than a new theory of space and time. It led to a nifty way of simplifying physics, by treating space and time as one thing, space-time. But Albert was just warming up. He wasn't happy with Isaac Newton's mysterious force of gravity. Naturally, he started work on his own theory. And sure enough, he cracked it. Mass causes space-time to curve. The natural motion of things is to follow the simplest path through space-time. But since objects with mass curve space-time, stuff moves towards the most massive object. That's what you feel as gravity. It's warped space and time that's keeping your feet on the ground. Warped space. Might sound too sci-fi to be true. We can measure the bending of starlight as it passes through the warped space around the sun. Warped time sounds even more ridiculous. But take an accurate clock to the top of a building and you'll see it runs slightly quicker than one on the ground. That's because as you move away from the centre of the planet, space and time are less warped. Most amazing of all, Einstein's theory told us that our universe has a beginning. Everything is expanding out from a hot, dense origin 13.8 billion years ago. But here's the catch. We've spotted that the universe is expanding faster than Albert's theory predicts. Could the old genius be wrong? To stick with his idea, we've had to invent a made-up energy, dark energy, to account for the speedy expansion. And we've had to assume there's an exotic form of dark matter we haven't detected yet either. These two unknowns should make up 95% of the universe, yet we've never detected them. That's the sort of thing that keeps physicists awake at night. So they're plotting some seriously big experiments to put Albert's theory to the ultimate test. For the last 100 years, Uncle Albert's great theory has passed every test possible. If it succeeds again, physicists will party. If they find its limits and it finally fails, they'll party too. Physicists are funny like that.
After the French Revolution erupted in 1789, Europe was thrown into chaos. Neighboring countries' monarchs feared they would share the fate of Louis XVI and attacked the new republic, while at home, extremism and mistrust between factions led to bloodshed. In the midst of all this conflict, a powerful figure emerged to take charge of France. But did he save the revolution or destroy it?
Order, order. Who's the defendant today? I don't see anyone.
Your Honor, this is Napoleon Bonaparte, the tyrant who invaded nearly all of Europe to compensate for his personal, stature-based insecurities. Actually, Napoleon was at least average height for his time. The idea that he was short comes only from British wartime propaganda. And he was no tyrant. He was safeguarding the young republic from being crushed by the European monarchies, by overthrowing its government and seizing power himself. Your Honor, as a young and successful military officer, Napoleon fully supported the French Revolution and its ideals of liberty, equality, and fraternity. But the revolutionaries were incapable of real leadership. Robespierre and the Jacobins who first came to power unleashed a reign of terror on the population with their anti-Catholic extremism and non-stop executions of everyone who disagreed with them. And the directory that replaced them was an unstable and incompetent oligarchy. They needed a strong leader who could govern wisely and justly.
So, France went through that whole revolution just to end up with another all-powerful ruler?
Not quite. Napoleon's new powers were derived from the Constitution that was approved by a popular vote in the consulate. Ha! The Constitution was practically dictated at gunpoint in a military coup, and the public only accepted the tyrant because they were tired of constant civil war. Be that as it may, Napoleon introduced a new constitution and a legal code that kept some of the most important achievements of the revolution intact: freedom of religion, abolition of hereditary privilege, and equality before the law for all men. All men, indeed. He deprived women of the rights that the revolution had given them and even reinstated slavery in the French colonies. Haiti is still recovering from the consequences centuries later. What kind of equality is that? The only kind that could be stably maintained at the time, and still far ahead of France's neighbors.
Speaking of neighbors, what was with all the invasions?
Great question, Your Honor. Which invasions are we talking about? It was the neighboring empires who had invaded France, trying to restore the monarchy and prevent the spread of liberty across Europe, twice by the time Napoleon took charge. Having defended France as a soldier and a general in those wars, he knew that the best defense is a good offense. An offense against the entire continent? Peace was secured by 1802, and other European powers recognized the new French regime. But Bonaparte couldn't rest unless he had control of the whole continent, and all he knew was fighting. He tried to enforce a European-wide blockade of Britain, invaded any country that didn't comply, and launched more wars to hold on to his gains. And what was the result? Millions dead all over the continent, and the whole international order shattered. You forgot the other result: the spread of democratic and liberal ideals across Europe. It was thanks to Napoleon that the continent was reshaped from a chaotic patchwork of fragmented feudal and religious territories into efficient, modern, and secular nation-states where the people held more power and rights than ever before. Should we also thank him for the rise of nationalism and the massive increase in army sizes? You can see how well that turned out a century later.
So what would European history have been like if it weren't for Napoleon?
Unimaginably better. Napoleon's seemingly unstoppable momentum would die in the Russian winter snows, along with most of his army. But even after being deposed and exiled, he refused to give up, escaping from his prison and launching a bold attempt at restoring his empire, before being defeated for the second and final time. Bonaparte was a ruler full of contradictions, defending a popular revolution by imposing absolute dictatorship, and spreading liberal ideals through imperial wars. And though he never achieved his dream of conquering Europe, he undoubtedly left his mark on it, for better or for worse. How did Adolf Hitler, a tyrant who orchestrated one of the largest genocides in human history, rise to power in a democratic country? The story begins at the end of World War I. With the successful Allied advance in 1918, Germany realized the war was unwinnable and signed an armistice ending the fighting. As its imperial government collapsed, civil unrest and worker strikes spread across the nation. Fearing a communist revolution, major parties joined to suppress the uprisings, establishing the parliamentary Weimar Republic. One of the new government's first tasks was implementing the peace treaty imposed by the Allies. In addition to losing over a tenth of its territory and dismantling its army, Germany had to accept full responsibility for the war and pay reparations, debilitating its already weakened economy. All this was seen as a humiliation by many nationalists and veterans. They wrongly believed the war could have been won if the army hadn't been betrayed by politicians and protesters. For Hitler, these views became obsession, and his bigotry and paranoid delusions led him to pin the blame on Jews. His words found resonance in a society with many anti-Semitic people. By this time, hundreds of thousands of Jews had integrated into German society, but many Germans continued to perceive them as outsiders. After World War I, Jewish success led to ungrounded accusations of subversion and war profiteering. It cannot be stressed enough that these conspiracy theories were born out of fear, anger, and bigotry, not fact. Nonetheless, Hitler found success with them. When he joined a small nationalist political party, his manipulative public speaking launched him into its leadership and drew increasingly larger crowds. Combining anti-Semitism with populist resentment, the Nazis denounced both communism and capitalism as international Jewish conspiracies to destroy Germany. The Nazi Party was not initially popular. After they made an unsuccessful attempt at overthrowing the government, the party was banned, and Hitler jailed for treason. But upon his release about a year later, he immediately began to rebuild the movement. And then, in 1929, the Great Depression happened. It led to American banks withdrawing their loans from Germany, and the already struggling German economy collapsed overnight. Hitler took advantage of the people's anger, offering them convenient scapegoats and a promise to restore Germany's former greatness. Mainstream parties proved unable to handle the crisis, while left-wing opposition was too fragmented by internal squabbles. And so, some of the frustrated public flocked to the Nazis, increasing their parliamentary votes from under 3% to over 18% in just 2 years. In 1932, Hitler ran for president, losing the election to decorated war hero General von Hindenburg. But with 36% of the vote, Hitler had demonstrated the extent of his support. The following year, advisors and business leaders convinced Hindenburg to appoint Hitler as chancellor, hoping to channel his popularity for their own goals. Though the chancellor was only the administrative head of parliament, Hitler steadily expanded the power of his position. While his supporters formed paramilitary groups and fought protesters in the streets, Hitler raised fears of a communist uprising and argued that only he could restore law and order. Then, in 1933, a young worker was convicted of setting fire to the Parliament building. Hitler used the event to convince the government to grant him emergency powers. Within a matter of months, freedom of the press was abolished. Other parties were disbanded, and anti-Jewish laws were passed. Many of Hitler's early radical supporters were arrested and executed, along with potential rivals. And when President Hindenburg died in August 1934, it was clear there would be no new election. Disturbingly, many of Hitler's early measures didn't require mass repression. His speeches exploited people's fear and ire to drive their support behind him and the Nazi Party. Meanwhile, businessmen and intellectuals wanting to be on the right side of public opinion endorsed Hitler. They assured themselves and each other that his more extreme rhetoric was only for show. Decades later, Hitler's rise remains a warning of how fragile democratic institutions can be in the face of angry crowds and a leader willing to feed their anger and exploit their fears.